So more simple machines. Stepping up in complexity, probably the next easiest machine is like a pair of pliers. A pair of pliers looks hard. And so this particular pliers basically says you've got a 15-pound force applied to the handles. That's your grip strength. Then what is the force exerted by the jaw on this bolt? And you go like, I don't know, how do I solve that guy? So this is a classic example of why a free body diagram is super important. Because you look at this the way it is, you go like, how do you solve that? That's not even solvable. But what you can do is just take 1/2 of this handle and just draw a real simple wireframe of that half. And let me get a piece of paper that I can do that with. I did it here, but I'll just do it again. So basically, you've got a line here and a line here. So you basically have a line here and a line here. This is 15 pounds. The jaw pushes on the bolt, and the bolt pushes on the jaw. So this is F bolt. And then there's pin reactions at A. So you basically have an AX and an AY. AX, AY. Your moment arms are 4.4 inches. And 1.2 inches. So notice what I did here. First of all, I took this complex shape and I drew a free body diagram, which is basically a wireframe. Don't be confused by, one of the things that is confusing about machines is that they have dimensionality to them. They have contours, they have interesting shapes. And you go like, man, how can I draw that picture? Well, one of the things you have to train as a static student, you have to train your eyes to do is don't be confused by all of the curves in the picture and reduce this picture to its simplest representation in statics. And just use straight lines. So this guy, we're focusing on this top half of the plier. And we do a straight line from here and a straight line here, which is this guy and this guy. We got the dimensions, we got the force, and we got the pin right here at A. Well, once you've drawn this guy, then you're just going to sum moments about A. So if you sum moments about A equal to 0, and you take 15, and notice how it gave the dimensions back to A. And so, I mean, the problem is screaming, sum moments about A, because they gave you the distances. And so 15 times 4.4, this way, minus F bolt, times its moment arm back to A, which is 1.2, is equal to 0. And we're summing moments about A, so AX and AY are not involved. In fact, I should have put AX and AY here, but I didn't. And so F bolt is equal to 4.4 times 1.2. I'm sorry, times 15 divided by 1.2. And you basically get 55 pounds is the bolt strength. So the force exerted by the jaw onto the bolt is 55. And that's also the force the bolt exerts on the jaw. So this looks super hard, but it's actually pretty straightforward. And once you draw a free body diagram, it unlocks the problem. This problem as is not solvable. But once you take it apart and draw a free body diagram of half of it, then you go like, that's a solvable problem. Because by taking it apart, you expose these forces that are in it. Since we're on this page, we'll work another problem. And again, this problem looks hard. And so this is like a Genie lift. You see these all around town. All of you guys have seen these. And I've kind of provided simplified dimensions of this guy. And so my boom extends out this way. There's a 300-pound load up here. We're assuming that the boom itself is massless. The overall angle, the boom to horizontal, is 26 degrees, right there. There's a hydraulic cylinder that connects down here in the frame and that it pushes up the boom. The angle between that cylinder and the boom is 20 degrees. Right here. And so the problem asks us to find what is the force in this hydraulic cylinder. What is that FB? And this could be a difficult problem depending on how you work it. But I'm going to show you the easy way to work this problem. And so once you see it, it's like, oh, that's really, really easy. And so there's a force FB that acts along the cylinder. So you've got the Genie lift, it comes up here, got the lift here. And then you've got a FB, looks like this. And then you basically have reactions here at A. But this is basically 20 degrees here. So basically, and this is 300. Basically, you can resolve this FB, since you're given the angle between FB and this member, you can resolve this FB into components along the member and perpendicular to the member. And so this resolves into an FB sine 20 and an FB cosine 20 right here. So now when I sum moments about A, the FB cosine 20 isn't in that moment equation. All I have is the FB sine 20 and his moment arm, which is 7 feet. And then I have the 300-pound force and his moment arm back to A, which is 14.4 feet. And so what looks like a super hard problem, as long as you have this angle right here, if this is theta, and this is like phi, this angle right here, if you have this angle here, this problem becomes super easy. Any problem like this is super easy. And we'll work another one like this too. And so once you sum moments about A, take clockwise to be positive, I have 300 times 14.4 minus FB sine 20 times his moment arm, which is 7. That's equal to 0. And so FB is 1.8 kip, or 1,800 pounds. So looks like a hard problem, but draw a free body diagram, think about it, know what you're doing, and it's like everything else. If you know what you're doing, then it's easy. So 2 pretty simple machine problems